Well, just welcome everybody to this wet and cloudy evening, which is going to prevent us from having one of our traditional star parties afterwards. I'm quite disappointed myself. I'm Susan Harder. I'm a founding member of the Hamptons Observatory. And I'm also a dark sky advocate. Some of you know me in that role. The observatory holds events throughout the East End, partnering with local organizations, such as tonight with the East Hampton Library. Our special speaker tonight, Dr. Charles Liu, is going to talk about all sorts of fun stuff going on in the night sky above us. He is a professor of astrophysics at the City of New York, an associate at the Hayden Planetarium with his colleague and our neighbor here in East Hampton, Neil deGrasse Tyson, who, when introducing Dr. Liu at Guild Hall, Dr. Liu, did you do a cartwheel or a somersault?
Cartwheel.
Onto the stage. He is the author of 11 books, and he brought his book that is not available here, which is available to you, The Cosmic Explained. He also hosts a podcast, The LIU-niverse. And as a globally recognized educator, he's received numerous awards and accolades. This talk is going to be posted on our Hamptons Observatory website. So now you can welcome the gentleman you've already gotten to know, Dr. Liu.
Thank you all so much. Thank you. Really, as you can tell, I'm very informal. This is a pretty technical talk and everything like that, but please consider this a conversation. I hope that you feel like as welcome as I do here in this library. I feel like I'm just hanging out. And so let's all hang out and have a good time and learn some cool science. Okay? The topic of the talk today is indeed how we map the universe, right? With these deep space surveys, we are making a revolutionary change in how astronomy has been done for a very, very long time. And what's super cool is that we as professionals are really excited to share all of this data and all of the discovery space with everybody. Astronomy, as you all know, isn't really a particularly profitable business. Right? You can't exactly sell or patent a star or a galaxy. Right? It's not going to do that. We're all curiosity driven. We're all wondering, and we're driven by the neat things out in the universe. And so we have been able, as astronomers, to convince a lot of people, governments and organizations, foundations, so forth, to support this work, much as people might have supported the arts or music centuries ago with patrons and things like that. But now it's us, it's the people, everybody, through taxpayer dollars and through donations and things like that, that make this kind of stuff possible, that make my job possible, right? A person who teaches for the fun of it, just for astronomy, not so that people can make money, but they can look up in the sky and go, wow, that's so cool. So you guys can all do it too. You guys are ready, poised, with all of these deep space surveys, to be able to make discoveries about the universe, all your own. All right? And you should. You should try it. You should start tomorrow. I want you to do that. So this is a talk about that. But first, of course, this is Starry Night. Starry, starry night. Don McLean. A beautiful picture. And when Vincent van Gogh first painted this, people didn't even recognize it. As most of you know, Vincent van Gogh was not recognized in his lifetime. And people, even today, look at this and go, is that the real universe? Is that the sky? Right? Now, he was thinking about the entire sky and how bright and how crazy it is. But a couple of my colleagues at the National Astronomy Observatories, specifically they were down at Cerro Tololo Inter-American Observatory in Chile, they took a picture of a spot in the sky recently, and it looks kind of like this. And it's kind of pretty starry nighty, right? They called it Starry Night Redux, right? Because you have the spots, you have the swirls, and this is what telescopes do for us. They allow us to look at the universe as if we had eyes that were 1,000, 1,000,000, 1,billion times more sensitive than our eyes actually are, right? I think all of us in this room would agree that there's nothing quite like going out in the middle of the night under a starry sky and seeing all the amazing stars. Now imagine if we could see it with 1 billion times bigger eyes, right? This is what we would see. And this is just a tiny patch of the sky too. So this beauty, this art, which Vincent saw in his mind, but not with his eyes 100 more years ago, we can see with our eyes today. And we have the pictures, we have the data, we kept it, right? Unlike us when we look up something and we see it once and that's it. I don't know how many of you have seen the Odyssey. It just came out last week, right? I've already forgotten a whole lot of it. But you don't have to forget anything in astronomy anymore because we've recorded it and we've kept it. Right? Now, as my wife will attest, I have a hard time throwing things away. You don't only need to look at my office or the basement to get actual proof of that. But part of it, I'd like to think, is because I'm an astronomer. And we astronomers, when we find something, we get a picture, we want to hang on to it. We don't want to let it go because you never know. Something that was discovered and a picture that you took 50 years ago, 100 years ago, 500 years ago, could come back and you study it today. And you realize, wow, that means that this particular star or this particular galaxy was doing that in the past. The time scales of the universe, all of that data matter, no matter when it gets taken. So the key is to save it and then be able to find it later. Does that make sense? Yeah, you guys all know that, right? How many thousands of pictures do you have on your phones? Then it's like, oh, we were at that wonderful place in Heather. Hang on, hold on, almost there. Well, anyway, so that's what we need to avoid. Right? So deep surveys today in astronomy have 2 big components. Component number 1 is the ability to obtain the data and to store it. And then ability number 2 is to find it when you want to find it. Okay. So how do we do all these wonderful things? The first really major big survey that I would like to talk about, the Deep Sky Survey, was done with this telescope. All right. Now the screen kind of zoomed it out a little extra. I don't mind, but this is a 4-foot across telescope. Okay, so the width of the primary mirror is 48 inches. It's on Mount Palomar in California. Now, most of you guys have heard of the 200-inch telescope on Palomar. Right? For a quarter century, it's the world's largest telescope, and it's really a big, beautiful thing. But this is not that. This telescope predates that 200-inch telescope, and it's only 4 feet across. But it can take a much wider field of view. This is called a Schmidt-Cassegrain telescope, and what that means is that the mirror is shaped in such a way that it can capture a broad field in the sky. So this thing can capture big swaths at a time, whereas the Palomar could only look at a tiny patch, very detailed and very clearly, but only a tiny patch at a time. So if you're trying to map the entire sky, you could take decades or centuries with something like a 200-inch telescope, but you could do it in just a few years with this Schmidt-Cassegrain telescope. So this Schmidt-Cassegrain telescope was built and finished in 1939. Obviously, it's had a paint job or 2 since then. But beyond that, the optics have stayed solid and have been well preserved and well used since the 1930s. Now, in 1948, the National Geographic Society, remember them? Right? Those guys. They funded something called the Palomar Observatory Sky Survey, using 14-inch wide pieces of glass that had chemical emulsions on them developed by Kodak Corporation. They would stick these big things right into the back over here and step across the sky, and they would get pictures of the sky in 2 different colors, one kind of a reddish color and one kind of a bluish color. Back then, you couldn't really say exactly what's RGB. Pantone hadn't set up all of its stuff yet. So everything was just kind of reddish and kind of bluish, but you would look across the entire sky. And for 10 years, it took these plates. In the end, more than 1,000 of them, different colors, and this became known as the Palomar Observatory Sky Survey. Beautiful stuff. I still used it. When I first started graduate school, I needed to find a particular object in the sky. I didn't know what it would look like. I'd be aiming at it with a little tiny field of view, like a big telescope like Palomar. So I would have to go to the plate stacks and use a little micrometer and take a look at these digital pictures of the actual glass plates and find the little dots, take a little picture with a big magnifying camera, and presto, you would be able to find the object you wanted. This sky survey was revolutionary, and we still have to thank the National Geographic Society for that foresight of having put together those plates. There's still some glass plates that exist today. By the way, that's Gene Miller. Okay, anyone here know Gene? Gene is an operator at the Ocean, it's named the Ocean Telescope now, OSCHIN, around, 2002, I think it was. It was renamed after this very generous donor. But Jean operates the Ocean Telescope. She's discovered more than a dozen comets and more than a dozen asteroids in her career. Very, very appreciated, and one of the people who does a lot of the work with that. And what I'll say is that this telescope, even after the Palomar Observatory Sky Survey is done, continues to do research because the Schmidt-Cassegrain ability to see lots and lots of stuff still goes on. Today, instead of putting photographic plates at the tip, they have a digital camera system, and the digital camera system allows you to take and retake and retake and retake. The current camera that's on that telescope, the 48-inch, has 570 million pixels. And it's called the Zwicky Transient Facility. Okay, and it's named after a Caltech astronomer named Fritz Zwicky, one of the first people who in the 1930s suggested that there existed cosmological dark matter. It turned out that he was such a jerk that no one believed him. But eventually the evidence bore out when a woman named Vera Rubin showed that it actually was true. And they were like, oh, Fritz, you were right after all. He's like, of course. But you know, that's another story. We'll talk about Fritz later if you want. But in any case, this would be an example of what the Palomar Observatory Sky Survey did, right? If you have this particular galaxy, it's Messier 106, otherwise known as NGC 4258, blah, 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 okay? Those little patches, you see this thing here and these things here, those are the pictures that can be taken with the Hubble Space Telescope, right? And you have to spend a lot of time in order to find those and take those pictures. You make a tile go across to see all those pictures, right? But this is only one tiny fraction of the entire Palomar Observatory Sky Survey. But what we did was, like I said earlier, we would go and find exactly where we aim our telescopes, and we point our other telescopes to look at it, and then map it out. So this is a modern version of that picture. Okay, again, before, right, after. And this is a multi-wavelength picture of the same galaxy. And the part that you could see before, right, the visual part up here, is the thing that you could see with your eyes in reverse color, you know, black and white reversed in the previous stuff. But now we have these blue streaks, which are from the Chandra X-ray Observatory. We have the purplish streaks here, like that and across, and those are from the radio telescopes, the very large array in New Mexico. And then these reddish blotches are from the Spitzer Space Telescope. So you take all these different telescopes, you stick them all together, and today's data allow you to stack an answer. And you can see the spiral arms are all wrong in the X-rays, right? We saw those beautiful spiral shapes in regular astronomy, in our regular optical eyes. We see these, but then you look and you go, wait, why are there these extra arms out there that don't seem to be lit up by stars, but instead are shining in X-rays and radio waves, right? It seems likely that the reason that happened is because right in the center there, which is all white there, there's a supermassive black hole, which is not uncommon, because we now know in the past 30 years we've learned that there are supermassive black holes in the centers of almost every galaxy. But this particular one seems to be spewing stuff like a garden hose that your landscaper forget to turn off. Okay? And it's been doing this for a really, really long time to spray all this stuff out. Can you imagine an environment like that, instead of like being a few feet across in your front yard, but this is in fact probably 500,000 trillion miles across. Okay? This is the kind of thing that we get to learn, that we can learn when we have all the data all the deep surveys, we put all the different data stacked up, not just looking at a pretty picture, but really understanding. And like, can you imagine what it's like out in the universe? We keep seeing things that we can't even imagine ourselves, right? When nature exceeds even our ability to imagine, I mean, it kind of turns what we think of as supernatural as just, oh, it's just natural. And it's super, right? It's pretty awesome. I think that it's a really, really neat thing to know. Okay, so as cool as that is, this is the more recent, okay? This is the next generation of what we saw with the Palomar Observatory Sky Survey. This is called the Sloan Digital Sky Survey. Some of you may have heard of this. The National Geographic Society was the one that primarily funded, as I mentioned before, the PAS, the Palomar Observatory Sky Survey. Well, a number of universities and their astronomers, led primarily by a guy named Jim Gunn at Princeton University, about 1980, started going around to different places and saying, hey, let's create a consortium of universities and observatories and ask a funding agency of some kind to give us the ability to do the next generation sky survey. Not just the Palomar Observatory Sky Survey, which was done with photographic plates, but now do it with electronic cameras, these charge-coupled devices. Back then, of course, charge-coupled devices, we were lucky if you had a few hundred pixels across each. Nowadays, you have millions of pixels every time you take a picture with your phone. But back then, even getting 1 million pixels was a big deal. And they said, okay, let's try to put this all together. And they created a consortium. There are dozens of universities and colleges and things like that all around the world together. And they were able to convince the Alfred P. Sloan Foundation to provide some funding to create this kind of telescope. Now, this telescope doesn't look quite like the other one, does it? But what it does is it tried to use all the best technology that was available in the late 1980s and 1990s to make the very best images possible. So the telescope literally has a roof that when the weather is nice, slides all the way off. Okay? So it's not in one of those mushroom-shaped domes anymore, but it just has its own building and it slides right off. And so when the weather is good, it's operating just in the open air. Meanwhile, all these baffles, right, these square pieces and so forth, are designed to reduce the amount of scattered light that bounces around inside a telescope in order to get pictures going down to 30 different chips. Not just one chip at the back of each of your phones, but 30 different chips. And the light would be divided and distributed across a wide variety of things. And then after that gets done, you take pictures of the sky, then you go back about a year later, or some years later, and start taking spectroscopic images, right? You've seen how spectra work, where you have, instead of looking at the sun, you see that there's one color. You split the light up into its component colors, and you see all the colors of the rainbow, and you see bright lines and dark lines, and that information is invaluable. That's the stuff that tells us about the atomic and molecular structures of the things inside the sun, for example. So we wanted to do that. And so Jim Gunn, brilliant man, and all of his colleagues and so forth, all put together this thing called the Sloan Digital Sky Survey. Now, I'm showing you this one picture here. See this round circular thing? It's about 3 feet wide. It's about this big, okay? And you'll notice that there are a lot of markings on them. It looks like crayon markings from maybe a grandkid at day camp or something like that, right? But believe it or not, that's actually what astronomers have scrawled on that thing. Because when you're taking a picture and you're using this thing in your telescope, it doesn't matter. These drawings do not negatively affect the data that you gather. But they guide us, because what happens is you notice that all these dots, this is just one example, see all these dots kind of all gathered around here. In each one of the spots where there's a circle, there is a carefully drilled hole right in that spot. And on the back side of it, you plug in a fiber optic cable. Right? And so each of these plates can hold hundreds of such holes. And on the back side, up to 640, if I recall correctly, fiber optic cables at a time in this big thing about, the size of 3 or 4 feet across. Then you put this in the telescope. Instead of getting a picture, then in each one of those little holes, you get a spectrum of the object that you're looking at. And so you combine that data, the spectra, with the images, and you learn all kinds of new stuff. Right? So the spectroscopic survey plus the visualizing, visible survey is the thing that's created this amazing thing. So here's an example of the data that's available. Okay? So do you remember I said you have to do two things? Once you have to get the data, and the second thing you have to do is to find the data. Right? So yeah, go ahead, good question. And come on up. I think there are some spots up here. There's two seats right here next to this person right here. Yes, what's your quick question?
That's why the car keys jokes.
That's why the car key joke works.
Yeah.
Right, because you can't find it.
I didn't get it at first, but I'm glad you explained it.
Yes. So the Sloan Digital Sky Survey came with, at the very beginning, and this was actually a big reason why the Alfred P. Sloan Foundation came behind it, because the Sloan Foundation's primary mission is to enhance and share with the whole of society knowledge, right? They don't ordinarily just try to do research, but they want everyone to be able to see it and to understand it. And so the scientists there, primarily led by a guy at Johns Hopkins, his name is Alex Saleh. He was a Slovakian immigrant to the United States, tremendously talented individual. And he said, basically, we are going to make all this data available to anybody. We're going to make it public so you can make it available. And as time has improved, we've gotten more and more skills at how to do databases. It is now at the 20th iteration of something called the Navigate tool for the Sloan Digital Sky Survey. You all can just go to that same website anytime you want, cas.sdss.org. Don't worry, I'll tell you later if you don't have to memorize it. But at cas.sdss.org, you can just type in the location in the sky of something you want to see. In this case, this is the right ascension, the east-west coordinate, and this is a declination, which is a north-south coordinate. You say, can you please look at this spot in the sky for me and see what's there? And you can just tap it, and half a second later, boom, there you are. Okay, and this is that spot right there in this area. So now this spot here, you can see this diagram. It says 2.255 by 1.525 arc minutes. Okay, so that's very small. If you held out your pinky at arm's length, it would be about the width of one of those little lines that show up if you don't eat enough iron or calcium. That's about 1 arc minute across. So this is a very, very small patch of sky. But looking at this object, you see that it is a very unusual and interesting object, right? Looks like a galaxy, but it's not really. There are two galaxies, actually, this one here and one here. And this one has been twisted and bent by the gravitational interaction that they've had coming toward each other. Right? This object is basically what we will look like in about 4 billion years when we hit the Andromeda galaxy. Okay, don't worry, it's 4 billion years, so don't change your retirement plans. We're good. But it's neat, right? You're like, wow, that's so cool. What other kind of data are available? Well, here is its spectrum. Remember one of those drill plates, right? You can look and see what its spectrum is. So if I wanted to, I could just tap on that with my computer screen, tap, and what is it? Well, it's this, right? This is a graphical display at the wavelength or the color of light that you're looking at, right? And then this is the strength or how bright it is. So this particular galaxy system, you can basically see that from 4,000, which is about blue to purple to our eyes, all the way out to 7,000, which is red to our eyes, okay? And then this part over here is near infrared, so we can't even see it with our eyes. But the telescope's cameras and detectors can see it just fine. What I can see is that in certain colors, we have really strong, bright lines. And all the rest of the colors seem to be about the same. But here, for example, at this spot, right at around 7,000 angstrom, which is bright red in our eyes, I see this incredibly strong line. That's the result of bright stars in that galaxy emitting so much ultraviolet light that it's knocking the electrons off of all the hydrogen atoms in the gas that surrounds them. When those electrons recombine with the protons to create the hydrogen atoms again, it emits red light at just that color. And this process is happening trillions and trillions of times every fraction of a second, over and over and over again. So it's pumping up this particular line to incredible strength. It means that there are lots and lots of young stars in these galaxies. So by looking at this graph, I'm able to know even better about not just how cool these galaxies are, but they're forming new stars. And within those new stars, new solar systems, new planets, and possibly even new life. Quick question?
Is this a snapshot or is this in motion?
Great question. Is this a snapshot or is this in motion? You have, can I pay you later? Because you perfectly led me into the next thing I was going to say. This is a snapshot of this galaxy. But the snapshot tells us that this object is moving. Okay? And the reason is, this picture is taken, you can see that at the top here, right? RA, the right extension, the declination, the position, where it is, and everything like that. And the class is a starburst galaxy. I just told you, like, new stars are forming furiously, right, because of this light. So the classification of this object is a galaxy that is having a starburst. It's forming stars at a rapid rate. But here's the kicker. Where this red line is not where it would be if we saw this very same transition in a laboratory. Here on Earth, if we knock off electrons from their protons, from hydrogen atoms, and let them come back together again, they will produce this line. But the line will be over here, where this little tiny dinky 0,1 line happens to be. This O1 line is actually shifted over from where it's supposed to be. This H alpha line is shifted over even farther. So every single line here is shifted to the red compared with what it would be in the laboratory. And you guys have probably all heard the term redshift before, right? What it means in this case, the redshift has happened. All of these different colors have shifted over in the redward direction of the spectrum. And that means that this object is moving away from us. In fact, it's moving away from us at more than 1,000 miles a second. Okay? The redshift number, Z, if you see in the upper left, Z equals 0.04, 027 plus or minus whatever, right? But that's a measurement that you can make off of the spectrum. And that Z number of 0.04 is a specific measurement which says that this object is moving away from us at a particular speed. It's at 0.04%, 0.04 fraction of the speed of light. Right? And that can happen either by a massive explosion moving that way, okay? But there's really no explosion in the universe that can move a galaxy that fast. So the only other reasonable explanation why this object is moving away from us so fast is because the universe is expanding. This particular picture is indicating not just the cool stuff before, but it's indicating that the universe itself is expanding, and that this particular object is a certain distance away from us being carried along for the ride. Right? It is amazing, right? Isn't it cool? Isn't, I mean, you know, I like this science stuff already, but I mean, if you asked me when I was, 20 years old or something like that, that I could look at something like this and tell you that the universe is expanding, I would never have thought that. This is so cool. What's your question?
So this is always phrased that this is moving away from us, but aren't we also moving away from it?
Yes. to be discussed later, but we'll go more into it in the Q&A if you want. But the bottom line is that everywhere in the universe is moving away from every other where in the universe. It's just this big expanding thing. And as a result, we here on Earth at this moment are in the center of an expansion. Just as somebody in Alpha Centauri is at the center of their expansion, just like somebody in the Andromeda Galaxy is the center of their expansion. So I don't know if your moms and dads ever told you this, but you actually are the center of the universe. Congratulations. Okay, we have a question back here real quick.
Very simple, parallel. Taking a snapshot
Yes.
6 months after the other snapshot.
Right.
Can they estimate how far away that is?
Ooh, great question. what is a way that we can measure the distance of an object without using redshift? Turns out that there is this thing called parallax, which you guys are, our brains use parallax when we use our two eyes to look at something to gauge how far away it is. You can imagine a grandiose way of using parallax, where you measure a location of an object when it's in January, and then wait 6 months, and in July, make another measurement and see how far away it is, right? You can use our entire width of our Earth's orbit as the width between our eyes, in a sense, right? That kind of parallax is very effective, and we can make excellent measurements of distances out to about 1,000 light years. Okay, light years is about 6 trillion miles, so about 6,000 trillion miles. But this object is more than 600,000 trillion miles away. So unfortunately, parallax is not able to get a distance here. Still, there are many different ways to measure distances, and this thing called the cosmological distance ladder uses redshift as one of those very, very important ways. Yeah, great question. These are excellent questions. You guys are bang on exactly the kinds of things that like we all ask ourselves when we were younger or when we were trying to learn about the size of the universe. So you can do this, by the way. I'll give you the website if you want later. You can go anywhere you want in the universe, thanks to the Alfred P. Sloan Foundation and all these colleagues of mine, to go and on this website find all this extra data that you want to, if you ever want to. And it's free to you all, right? So whatever taxes you've paid before to support your local universities and so forth, this is one of those benefits that you get back. And there have been many, many discoveries by many people, not just professional astronomers or astronomy professors and so forth, using these kinds of databases, and the Sloan especially, tremendous. The Sloan Digital Sky Survey is now in its 5th generation. It's been going on for more than 25 years. Like I said, this is the 20th iteration of the data release that you can go online and find with this thing called Sky Server. And my students, my undergraduate and graduate students, are using this tool all the time. Really, really neat stuff still happening. And so, this is a great deep sky survey, but we're still not finished yet, because this telescope is doing the next great sky survey. All right, and I want to tell you about this a little bit. This is called the Vera Rubin Observatory. You might have seen, this is the picture that was on the cover of the webpage for today, right? This is in Chile, in the Atacama Desert. All right, it's about latitude of -30 on the Pacific coast of South America. And what's really cool about that is the way that the ocean currents and the winds work, the whole El Nino, La Nina type stuff, it steers the rain and the clouds away from that coast. So this is some of the driest, some of the least rainy areas in the world. On some of these mountains in the background, there has not been rain recorded on them at all, ever, okay, since modern meteorology. All right, so it's really quite amazing. So in this area, we have to pick the mountaintops that we can get to that are accessible, that are not so far away that we can't get to them, have roads, and also are appropriately in areas that are not, say, sacred. There's a lot of work with like indigenous people and native folks in this area. The astronomers worked very hard over the past couple of decades to try to make sure that everything is done well. So we picked this mountain right here, Cerro Patron, and this telescope, remember the Schmidt telescope on Palomar was about 4 feet across, right? And then the other one, the Sloan Digital Sky Survey telescope, is about 12 feet across. This one is 27 feet across, okay? And it sits in the top part here. That part down there contains all of the equipment. Instead of having to put those plates right on the telescope, which makes it very, very difficult, right, because they're very heavy, now you take all the stuff, you put it in a single camera, you use fiber optics to send it into a computer control system over here. The camera has 3,200,000,000 pixels in it. It takes a picture every 45 seconds, and it just keeps taking a picture of the sky like that. And operations just started at the end of June. on Monday, June 29th. Okay, so more than 100 gigabytes of data are being obtained every night. All right, every night. So I don't know if you guys know how many gigabytes your phone has, but it overflows on a regular basis. And because they're taking these pictures every 45 seconds, you have a data rate that far exceeds any wireless internet thing that you might get from whatever service provider you get. So all of the stuff down here is basically equipment that sends the data via something even faster than the internet. It's like super extra dedicated internet, 2, 3, stuff like that, to data centers all over the world. One in Chile, one in Germany, one in the United States, one in the UK, I think. I think there's also a second one in the United States in California. But the combination of all this is you're sending all the data out all the time, so that if you see, say, a star blow up, you see it 45 seconds later, a spot that was kind of small suddenly is really bright, and then 45 seconds after that, it's 10 times brighter or something like that. Whoa, there's something just exploded. You send that information through all of these data centers around the world to other observatories. And so not just using the data you have here, you say, wow, check out this new thing. And then those folks, which are standing by, right, they're all over, they point their telescopes to that spot and start watching the telescope as it records in real time the explosion of a star or the collision of a galaxy or those kinds of things. It's really, really amazing, all right? We started this thing, the alert broker, the thing that changes how many times you find something changing over the course of the night. We expect to get more than 10,000 new discoveries per night of changing things. There's no way we humans can possibly keep up with that. There are only about 8,000 professional astronomers in the United States. And by professional, I mean like someone actually like makes a living doing astronomy research or hardware or software or something like that. So it is absolutely your responsibility, all of you, to help discover things about the universe. And it is possible. The Rubin Observatory is named after Vera Rubin, the person who, remember I told you about Fritz Zwicky, right, who discovered dark matter, we think, but no one believed him. And then Vera Rubin came back and said, no, actually, it turns out Fritz was right. So Rubin really revolutionized our field, extremely important individual. So the Rubin Science Platform, notice how different the previous platform looked. Remember, it was like, it's all very technical and digital, whatever. This is just the beginning of the Rubin Science Platform, okay? There isn't just one. There's a portal, and then there are what are called Jupyter notebooks. Have you guys ever, I don't know if any of you use Python. It's a technological computer kind of program system. But unlike our previous, like when I learned how to do programming, right, where you had to type a computer program and then it would do exactly what you told it to do with that. Nowadays, you can use these things called notebooks, and you write a little bit of computer code, and it does the thing you ask it to do. And then you write a second code, but instead of rewriting the code, you say, okay, do the same thing you did before, but change this. And it'll do that. And then, oh, do this and change that. It'll do that. And so you're basically building, your computer program is much more powerful than it used to be. And this isn't even AI, okay? We're not talking about some non-human telling you what to do. The human being is changing these things in real time. And so these have evolved to a place where the data are no longer static. On a matter of time scale of days, hours, or even minutes, you can tell your computer program to do something new, to make a new discovery, to find a new analysis over and over and over again. You can do that all night, every night, as long as you can stay up at night. You can do everything that you want. And then the notebooks are there. The APIs, how many of you have used an API before? Yeah, an API is basically an interface where you can access a computer database without going through a human being. All right, you can just type in and say, hey, hello database, please give me all this information. And then load it onto the computer, or from that computer, actually do stuff without having to move anything around. So this is, I haven't shown any of the technical screens and so forth. There's no need to do that. But just realize that if you guys want to, you can spend a little time learning these techniques. Go into the portal of the Rubin Science Platform. Load these notebooks. Learn how to type these things. And then start making discoveries using the API, but querying the database every night if you want, and finding new stars that are blowing up, finding new systems that are changing on a night's basis, finding new categories of objects that we haven't even thought about yet before. Okay? This is all there, it's all available at the rate of 100 gigabytes per night, all right? At the rate of as much as you ever want to do. And we haven't thrown any of it away, right? It's all there. And it's gonna go on every available night, not tonight because it's cloudy, right? But every clear night for 10 years, right? So the database it produces will literally be a 10-year-long movie of the night sky. And all of you can do it. Any of you are welcome to go to the Rubin Science platform, get an account, or get your grandkid to get you an account. That's fine too. And you guys can start making some of these discoveries and say, hey, I'm curious about this. Can we learn? So this is a great thing to do at night when it's cloudy or it's raining. You can make your discoveries because it was clear in Chile on an August night in the year 2026. All right. It's really, really quite amazing. Did you want a question real quick or wait?
Do I need to know about how to use Python?
Do you know how to? Do you need to know how to use Python in order to use this stuff?
Yeah.
Great question. No. You can, if you want to. You can learn this Python stuff yourself, and then you could do even more stuff. But there is now a platform. You may have heard of something called Citizen Science. The Rubin Observatory has partnered with the Zooniverse as a group of people, and you can just go to that website and start working on Rubin data without having to learn a single line of coding. You can just say, hey, can you use your brain, please, to help us manage all these databases? This galaxy, we have 100,000 galaxies that we need human eyes to look at to see if they look unusual or if they look okay. Would you be willing to do that? And there have already been many, many discoveries along those lines. But people have been using it to find comets, to find asteroids, to look for exploding stars, to look for colliding galaxies, to look for supermassive black holes that have flared because they've absorbed a new piece of a star. It's all there. So you can do all of that if you
So
want.
this is really like a recruitment camp.
Oh, you noticed. Yes, you recognize it. What I'm actually doing here is trying to convince you to do the work. Yes, absolutely. I do want to tell you all, this is a recruitment thing. Not because you'll bring me fortune and glory, but because we will learn more about the universe if you do it. And it's yours. If you actually discover a new comet or a new asteroid, they'll name it after you. Okay? And by they, I mean the International Astronomical Union. But you don't have to wait for them. You can just say, hey, I discovered this. I'm going to call it George. And that'll be fine. And that'll be an unofficial name until it becomes official. Yeah, so there's a lot that you can discover.
So just a follow-up question.
To follow up real quick, yes?
Real quick, if I go on here and I start getting into it,
Yeah.
is there a back end where people are watching what I'm doing?
If you get into it, you start going forward.
Governments and
Yeah.
stuff?
If you find this, no one is looking at it because there isn't enough money for somebody to look at it. In other words, there are no astronomers or government agents kind of watching you, all right, to see what you find, because it's all open and free and federated. And what happens is, if you find something cool, then you can say, hello, I found something cool. Can someone take a look? And then a person, usually a volunteer, possibly a scientist of some kind involved in the project, will look at it and say, yep, that's something new. Or, well, that's a lot of people have seen that kind of thing. Thank you for your contribution. So you will sometimes contribute a small bit. Sometimes you'll make a big contribution. There's a very famous example that a lot of us astronomers like to talk about the previous survey, the Sloan Digital Sky Survey. Right? Remember, this Rubin Observatory, this first surveys only started last month, so we don't have anything signed like this yet. But there was a Dutch high school teacher named Hanny van Arkel, who Hanny was doing this citizen science work and just looking at galaxies and trying to find structures. And then she said, hey, there, in this particular picture, there's this weird blob here. That doesn't look like anything I've ever seen. Is this real, or is this a piece of noise, or what is this? And so she sent that into the Galaxy Zoo or the scientific community. About 5 minutes later, another scientist it was daytime at that time for that scientist, because she was doing this at night, in the evening after she had taught everything. That scientist took a look at that thing and said, yeah, this is real. This is not, fake data. They went into the database and confirmed that it was actually an actual thing and not just some piece of noise or stray light. Turned out that this object that Honey had found was a blob of intergalactic gas that was thousands of light years across, that had been lit up by the ultraviolet radiation that had come from a supermassive black hole more than 1,000 light years away. And it's amazing, right? You're like, what? It's just a human being, you and me, right? Just looking at a picture going, wow, that looks cool. Could that be something astronomical? Chance favors the prepared mind. The system was built so that they could look at it. 99 out of 100 times is not going to be something new, but Honey found something that no one else had ever seen before. And that object today is called Honey's object. Okay? Honey's voorwerp, because I guess in Dutch, voorwerp means thingamabob. Okay. So there's your answer. Yeah?
Another follow-up one?
Mm-hmm. Sure.
So this portal is global, and it's all in English, or there are translators in the
Global
middle?
in English and Spanish, and in other languages in certain specific things as well. And nowadays you can actually, people are working, I believe, on trying to make it so that you can put this in a real-time translation via a large language model in AI, something like Claude or something like Google Gemini or something like that. So all of that is happening. It's happening very rapidly, and you guys are all living through that opportunity to do it. Okay?
In the first month.
In the first month, yeah. Yeah, you got a long time left to go. Okay, so I'm at 40, 41, 42 minutes, so I'm going to finish up quickly by telling you guys that there's even more that you can do. Okay, this is the stuff that hasn't been launched yet. This is just one piece of how a comet was tracked. This is Comet 3I Atlas, which was found to be an object that came through the solar system from a different solar system. More than 4 billion years ago it was found, and it's just moving across. And Rubin saw it in its test phase. Not even in the past month, but like a year ago, while it was testing, it actually, by coincidence, found that very object. Right? It's not an alien spacecraft, don't worry. But it really is a very, very cool object. That's just an example of one of the things that you could do, you could find if you felt like doing it. And that's just something that happened even during its test phase. So in my final few minutes, I want to introduce you to Nancy Grace Roman. Nancy Grace Roman was a very talented astrophysicist, but unfortunately, after she got her PhD, no one would hire her because she's a woman. Okay, this is in the 1950s. She was like, oh, bummer. But she was able to get a job at this new thing called NASA in 1958. And again, this is one of those great stories. As society was moving forward, astronomers and scientists said, we're going to bring all comers. We don't care about the past prejudices. If we can help it, if you're good, come do stuff. And unfortunately, Nancy Grace Roman was never quite recognized as she should have been in her time. But fortunately for all of us, she kept doing the work anyway. And she became known as the mother of Hubble Space Telescope. She was the one who published the first paper suggesting that you could use a planetary telescope orbiting in space to find other planets around other solar systems. She wrote that scientific paper in 1958. And then she was working with NASA the whole time to build first little tiny telescopes that was in orbit, and then slightly bigger ones, and then finally the Hubble Space Telescope, which launched in 1990. And it is surprising to me even, almost a little embarrassing, that I didn't even know who Nancy Grace Roman was until about 10 years ago, when it was announced that we would name a space telescope after her, in honor of her work as the mother of Hubble and all these other space telescopes. So it's called the Nancy Grace Roman Telescope, and these patches here, I just wanted to show very quickly, they're here because it's demonstrating that the Nancy Grace Roman Space Telescope, which is hardware-wise every bit identical to the Hubble Space Telescope today, can actually take pictures at a rate more than 1,500 times faster than Hubble. A combination of that technology that was used in the Schmidt-Palomar surveys that we could see large swaths of sky, was added in using software and secondary optics. And then the computers are so much faster now than they used to be in the past, that now, 35 years on, the Nancy Grace Roman telescope will be able to work at a speed that so far exceeds Hubble that within its first month, it will gather more data than Hubble has in its entire 35-year service life. It's amazing, amazing stuff. And I was at the American Astronomical Society meeting in Phoenix. This is just a picture of Nancy, and then there's the Hubble in the background. This was taken a few years before she died. She passed away in 2018 at the age of 93. But about 2010 or so, I think there was a picture she was taken. This is the Air and Space Museum, the NASA Hubble Space Telescope picture there, or NASA Goddard Space Flight Center, one or the other places of this model. But the data here, I was at this meeting, science meeting, and my NASA colleagues are planning to make all of that data public as well. Okay, it's all going to be available as soon as you guys are ready. It's going to require a little bit more tweaking because the Rubin system and the Sloan system have been worked on for so long. They're smooth, you guys need. It's going to take another year or two for you all in the public to be able to use the Nancy Grace Roman Space Telescope data. But that telescope is scheduled for launch on August 30th. This will launch, it will fly into its orbital station. It'll take about 6 months of calibration, and then it'll be starting taking the data like this. It'll be amazing.
It'll be in the same portal?
It'll be in a related portal. Not the same portal, but a very similar portal. And then you will be able to run it right off of the servers at NASA. You won't have to download anything onto your own computers. Everything will run there. All the software will be there. And you guys can start making discoveries as soon as that becomes available too. So let me end with this picture. This is Vera Rubin. When I was giving a talk at the State Museum of New Jersey about a year and a half ago, a person came from Philadelphia and said, I came to your talk specifically because Vera Rubin is my cousin. This is a picture taken, we believe, in Philadelphia around 1938. And Vera is the 10-year-old girl here. And this is a family photo that this cousin had taken a picture of and said, yeah, this is something. And I said, can I use this? Can I show this to people? He's like, yes. Now, there isn't anything, say, astronomically significant about this, right? I mean, obviously, this is a really extreme close-up of the universe. So in that sense, it's kind of neat. But for me, as a professional astronomer, I have always felt that the most important part of astronomy is us, right? The field of astronomy isn't some grandiose blob of data that we all are trying to find out about the universe. It's all of us doing this stuff, wondering about the universe and going, this is neat. I wonder what I can find today. And so, in a sense, I don't think 10-year-old Vera could have imagined that she would have the world's most advanced telescope named after her, after she had confirmed the existence of cosmological dark matter, after she had done all the things she did in her life. And you think about Nancy Grace Roman, you think about Gene Muller, all these people behind us who have done all this incredible work. And that's what inspires me, perhaps more than any other individual discovery, any other supermassive black hole, any other new picture of a distant galaxy, right? Astronomy is us. This is the stuff that we do. And I am so privileged to be able to do this for a living. People actually pay me to do this, right? But even if I weren't paid, I would find a way to do it in my own spare time because it's fun. Well, now you can. You have a chance in your own spare time to make discoveries as cool, maybe even cooler than what I could make during my regular day job. I want you guys to do it. I want you all to feel like you're a part of it. I want all of us to feel like we can be people who are studying the universe. And so please enjoy that feeling, all right? And know that you are welcome and available, and we're recruiting you anytime you want, okay? Come on over, we'll sit down, we'll sit at the computer, we'll learn how to use these tools. So with that, thank you. Please have any questions for me. I would love to tell you more about all of this great stuff that we do. Thank you. Question over here. Oh, is there another microphone that maybe we could share? Then we could bring people around. Go ahead with the first question.
just interested that when they first discovered the universe was expanding, they thought it would slow down slowly, but now they know that it's actually speeding up.
Right.
And
Right.
they attribute that to this dark energy.
Mhm.
We were down at the McDonald Observatory in
Ah.
West Texas, the darkest place on Earth.
Mhm.
And the telescope is doing what the Rubin does, but it's not as advanced. But
Yes.
have they gotten any hint as to what this dark energy is?
Ah. Do we have any hint as to what this dark energy is? Yes. Let me tell you. A bunch of my colleagues, led by Daniel Eisenstein at Harvard, have recently completed phase 1 of what's called the Dark Energy Spectroscopic Survey. Okay. They measured the redshifts, that is the motion, right, that we're talking about, the expansion universe, of 47 million galaxies, ranging in distance from a few million light years to more than 10 billion light years away from Earth. With that many galaxies, what they were trying to do was to get statistical information, right? Trying to figure out large-scale patterns of behavior in the universe and how that all works. And the goal was, indeed, to map dark energy on a very detailed scale to see what's there. So we still don't know what dark energy is, but this survey has started to give us the first hints of how that dark energy distributes itself as a function of cosmic time. How much dark energy was there early on? How much there was, say, more recently? How much is there today per cubic inch, for example, of volume of space? How much of this energy is there and how is it distributed? And what it looks like is that the nature of dark energy is changing with cosmic time. Instead of being this cosmic constant, which was what Einstein thought it was, a cosmological constant, it looks like a cosmological function of time. So this is giving my theoretical colleagues all kinds of enjoyment. They're like, wow, we don't have to assume that the cosmological constant is constant. The dark energy of the universe is changing with time. That is the latest on that, and it's very, very cool. Thank you for that question.
Decreasing or increasing as you go out?
Is it increasing or decreasing? As time goes on. It looks like it's increasing with time. However, the error bars are not quite there. If you do the statistics, it could go either way. We do know that with at least 95% certainty that it's changing. But exactly how and whether it's changing only in one direction or if it's been going up and down, that stuff is still unclear.
Is it uniform in all directions?
It's still uniform in all directions at the moment, yes. So the expansion is still true. And there's one more question in the back. Right, just hold the camera right there. No.
I was just wondering when the survey started, and will you come back and tell us more about the results?
The DESI survey started about 5 years ago. Phase 2 has begun. And so they're probably going to release another, maybe not 47 million, but many more millions of spectra in the next, I think it was 2.5 to 3 years. And in the meantime, they will continue to reanalyze the data that they already have from the 47 million. And I would be happy to come back. We'll rock and roll. We'll have fun. Okay? All right. As a microphone is going that way, and then we'll come back over here for this question. Yeah, go ahead.
All right, pedestrian question here. Orbital telescopes would
Yes.
seem to be superior to terrestrial telescopes, full stop, right? Are we at the point where we shouldn't invest in any more terrestrial stuff because we have the ability to just, put everything up there?
That's a great question. And the answer basically comes down to cost. Okay. The largest space telescope that's currently out beyond Earth is the James Webb. It has a mirror, it has an umbrella-shaped mirror. It opens up like an umbrella. And its mirror right now is 6.5 meters across, or about 21 feet across. And that telescope costs $10 billion. And it costs more than $1 billion a year to operate. Okay? So that's a lot of tax dollars. The Rubin Observatory, which I've been talking about here, it's on the ground. It's in Chile. It is 27 feet across, so it's substantially larger than the James Webb. It cost 1.3 billion to make, so less than 1/7 the cost. And its operating budget is about $200 million a year. So that makes it about 1/5 that of JWST. So in that sense, there is a huge cost differential. We can do not quite the same data, gather the same kinds of data, or do the same kind of scientific research with the ground-based Rubin as we can with the space-based Webb. However, there's a lot of different research to go around. And so there's a lot of science that still can be done on the cheap compared to being out in space of the ground-based telescopes. And then there's a more subtle thing too. We've had a really long string of tremendous successes in space. The Hubble Space Telescope is the leading instrument of our generation. The James Webb is running so well that NASA had expected it to run for 5 years. It looks like it can run 15 to 20. Right? It's just amazing. But things do go wrong. And if you're 1,000,000 miles out in space, you can't fix it easily. If something goes wrong with a Rubin, someone drives up with a pickup truck and a wrench, right? So in that sense, you're also giving yourself a little bit of cushion. If something goes wrong, being on the ground is much easier to fix. So these are the trade-offs that we do. And so we do have to be careful, right? Our Earth is a limited resource. So we're going to keep putting stuff on Earth, or even in low Earth orbit, which is also a limited resource. We need to be wise and know how and what trade-offs to make. But at the same time, we should continue to look at these off-world technologies because, darn, they are good. Thanks.
Something very
Uh,
true.
I was gonna
Back
ask
over
you
here.
a question.
Oh, same question? Oh, thank you for that. Okay, go ahead. Yes, this person here, and then let's go back in the back again.
So, what were the major puzzles in astronomy that these sky surveys are directed at? So when you got money for them, presumably you were telling the funding agencies, these are the problems that we,
Yes.
the great puzzles of astronomy.
Yes.
And we think we should be able to learn something
Right.
from this device.
That is a great point. When we are trying to find funding for big surveys like this, we want to answer big questions, right? So, for example, the Sloan Digital Sky Survey's original pitch was that by looking at across the sky and measuring all these objects, then we would be able to figure out the large-scale distribution of matter in the universe. And today, you often hear about this concept of the cosmic web. Right? We all kind of hear like, oh, galaxies are arranged in a web that's three-dimensional across the universe, and it looks beautiful like a spider or a fractal pattern or something like that. It was the Sloan Digital Sky Survey that laid the groundwork to make that discovery possible. But at the same time, while it was doing that, it also found all kinds of really cool new objects, right? Entire classes of supermassive black hole systems that we've never known existed before. Galaxies with very unusual properties, stars and star clusters arranged in ways around our Milky Way that we never knew could happen. So you were finding a lot of other things that were unexpected, that our prepared minds had to be ready for, for example, right? So the big ideas are what get sort of the projects off the ground or open to the sky. And then the individual discoveries that you all can make, for example, that maybe I hope I'll make as well, are the smaller ones that come from there. So something like the Rubin is basically going to try to find out over 10 years, how often do stars blow up in the universe? How and where? Did they blow up more often in the past than they did in the present? And if so, how much? And how does that mean, what does that mean for the history of the universe? How our own galaxy or our old universe is aging as cosmic time. That's Rubin's main thing. Excuse me. And then Nancy Grace Roman Telescope is basically doing what Hubble can do, right? But 1,500 times faster. So the gain that you have there is, we think of Hubble as making the most discoveries about the universe per month of any system ever invented. Now imagine it 1,500 times faster. And that's kind of what we're hoping for. So I hope that answers the questions on the most broad things, and then on narrow things there's a little bit more. Yes, go ahead.
One kind of technical question you might not have in your head right now, but the Rubin telescope out of Cape Canaveral, I assume, do we know what vehicle that is and what trajectory it's going to take? Because we've had a lot of success on the bluffs at Montauk seeing shuttle flights.
Wonderful.
Especially at night.
Yes. The Nancy Gross Rubin telescope will be launched August 30th from Cape Canaveral in a SpaceX Falcon Heavy, I think. And it is already on the pad. It's going to go in its own main things. If the launch vehicle works, it'll be great. And it will be sent to the L2 Lagrange point, about 1 million miles away from Earth, where much has been made, by the way, of the L2 Lagrange point. It is not a point. It's a big patch of sky. Okay, and what it is the actual Lagrange point itself is a spot that is in a straight line between us and the Earth and the sun and the moon. Okay, you can draw a line between the sun through the center of the Earth, past the moon, about another 750,000 miles, and this is called the L2 Lagrange point. Any object in that spot will orbit the sun as stably as the Earth does. So that's great, right? All you need to do is to have little tiny thrusters that will keep the spacecraft orbiting the L2 Lagrange point, and that thing could last as long as you have fuel. You don't have to worry about like corrections of their orbits and tweaks and this and that. All you need to have those thrusters. And so what happened was that the James Webb, the telescope with its original rockets and its original launch, was placed in such a good spot around the L2 Lagrange point that its thruster fuel will last at least a decade longer than people thought they would. So that's the kind of gain you would get from that sort of thing. I hope that answers your question, sort of. I hope, indeed, on August 30th, it'll be nice and clear. If you guys go out to Montauk, you should be able to see a shuttle, not a shuttle flight, but the launch coming out from Cape Canaveral.
That Falcon Heavy, when he uses it to put up the Starlink,
Yeah.
etc., the ones that are on the same trajectory as the International Space Station, about 51 north.
Wow.
They come right up the East Coast. They
Really?
go to Nova Scotia, and you can see them separate.
Wow. Well, you guys definitely make a plan for that. Okay? Take some pictures and send them to me. I can't wait. Yeah, August 30th.
And it's got to be at night.
Oh, that's right. I don't know what time it is.
Well, it doesn't have to be.
Okay.
That's much more.
It's much easier to see, right? Yeah. Wow, that's fantastic. Yes, take advantage of that incredible location resource that you have. Absolutely. Okay. Another question over here? Yeah. It's 8:07. I'm okay staying. You guys good? I think, yeah, okay, let's keep going.
Dr. Liu, I just wanted to say thank you for the lecture. It was really excellent.
Very welcome.
And in the interest of open science, I don't have a question, but I would just hope if you wouldn't mind letting me tell people about 2 different opportunities they have to pursue open science.
100%, please do.
Thank you so much.
Who are you, by the way? You should tell us who you are so that we can find you as well.
Yes, so my name is Michael Caprio. I work at Nikola Tesla's laboratory in Shoreham, just over in Brookhaven. So this is Tesla Science Center at Warrenclyffe. So for the last 2 years, we've hosted a NASA challenge event called the Space Apps Challenge as Space Apps Brookhaven. That's our local site. So just like Dr. Liu was saying about APIs and data, NASA has been producing this event for almost 14 years, and 180 countries all over the world and hundreds of thousands of people have taken part. And they work on solving problems for NASA. And no one has to have any special set of skills, but you can work with APIs, you can work with data, and you just, whatever skills you have, you bring to the table and you work with teams over the course of a weekend. We actually held it in New York City as well for 5 years. We had astronauts visit and a whole bunch of cool stuff. So that's the first thing. So we will be hosting that at Tesla Science Center in November 14th and 15th this year. The second thing is, there's a project from the American Museum of Natural History called OpenSpace. Anyone can download OpenSpace from openspaceproject.com, and it's basically the same planetarium software they use at the Hayden Planetarium and in many other planetariums all around the world. It is the next generation of data visualization for space. You can go all the way from the surface of the Earth out to the ends of the universe. You can explore different missions like the Curiosity rover on the surface of Mars as if you were actually there. It's very easy to use, a very intuitive tool, and you can download it on any laptop that has like a decent graphics card on it. So openspaceproject.com and Tesla Science Center. Thank you.
Thank you so much for telling us. I will be there. Applause, yes. Woo. That, by the way, is what I call type 1 applause. It's the kind of applause you give like when you're being introduced, you know, like someone's being introduced and you don't know who he is and they're just coming up to talk. So like, oh, yay. And then type 2 applause happens when the person talks and like, oh, that was pretty good. Yeah, hey, all right. And then number 3, type 3 applause happens when that person happens to be your brother. Like, whoa! Anyway, great. You are type 3 worthy for sure. Thank you so much. Okay. All right. Yeah. We have another question here up front. Yeah. Here comes the microphone.
Hi there. So my son is a student.
Excellent. How old is this student?
He's in 18th grade.
That's a great year. I had a good time in 18th grade.
He found when we were coming here, and he said, "Oh, I've got a deep space mapping question."
Deep space mapping.
I think he understands that your research right now is on early universe analysis.
And how does he know that?
He looked you up.
Oh no. Okay.
While we were going.
While we
through
were
the
talking.
jokes.
Okay.
Yes.
All right. Okay. All right. Hold the microphone close so we can all hear what you're saying.
There's a paper from February 3rd that he gave a journal club presentation on that was published by Kaifeng Zhu and Xin Wang.
Mm-hmm.
They used machine learning strategies that he has since built into his thesis to reconstruct the BAO oscillations measured by deep sky surveys from simple 21 centimeter curves.
Mm-hmm.
Their work implied that the universe was far older than our current Hubble metrics imply. Would you be able to address the huge discrepancy between computationally learned Hubble time and analytically calculated Hubble time?
Yes. But first, who is this precocious 18-month-old child of yours?
He's actually going to be 23 next week, and he's in his second year of grad school at Florida Tech. His name is Colin Harrison.
Colin Harrison.
He was an astronomy, astrophysics major, and now it's space.
Okay. Where was he before? Where was Colin before? Before he went to Florida Tech?
He was in East Hampton Library.
Excellent. Okay. All right. Good. All right. Tell Colin the following. That paper is wrong.
The paper he wrote?
No, the paper he did a journal club on.
Okay.
He didn't write it. He gave a talk. He said he gave a journal club on.
Right.
Okay. What that means is, this is all technical speak, okay? But what basically happens is when you're a graduate student and you're in a department, one of the things that graduate students do, usually about once a semester, is they read a paper that has been published and they give a talk to the faculty and their fellow students at a lunch. So people are munching away at their granola bars or whatever. And then this guy says, okay, well, this paper published by blankety blankety blank did this and this and this to find that, that, and that. Does that make sense?
Yeah.
And so this is like their practice, so they learn how to read scientific papers. And also it gives an opportunity for the faculty to hear new things that are happening. Okay. So this particular paper, yeah, okay, I know you're going to be sending this to Colin later. Hi, Colin.
Because he's the center of our universe.
Yes, absolutely. Colin, that's a great paper to give a journal club on because it's wrong. And the idea is, could you figure out where they went wrong, right? That's the thing that has to matter. When you use AI these days, all right, what's going on is that you are feeding it information, but it only looks at stuff that has been published before to try to use that information to conclude things. Now, they use the BAOs, okay, those are called the baryon acoustic oscillations. These are vibrations that were set up in the space-time of the universe just after the Big Bang. Those were measured using DESI, this 47 million galaxy survey, and humans, not AI, right, humans using AI, were able to figure out how those oscillations showed that dark energy was changing with cosmic time. However, if you use AI incorrectly, you can use those baryonic acoustic oscillations to match up scientific models that have no bearing on reality whatsoever. Okay? Now, it doesn't mean that it's not worth doing, right? But if you publish a paper and you get something seriously different, you have to ask yourself, what went wrong? If absolutely nothing went wrong, then you have made an amazing discovery. But at the same time, you have to explain why everybody else is wrong, right? So that's what we're looking for. So please find out what they did wrong and then tell us all here at East Hampton. Thanks, Don.
And just to follow up,
Yeah.
his presentation won first place at this particular place.
Awesome.
So,
Well done.
yes.
Glad to hear it. So
Thank you.
thank you. No, this is wonderful. I'm so glad that this is what's going on. So those kinds of discoveries are things that really need to be thought about. Okay, I think we have time like maybe one more question, and then I wanted to be in the back. The East Hampton bookstore, unfortunately, could not get copies of my books in print in the United States on time. But I was able to get stuff like from my attic of a book that was published a couple of years ago by a British publisher. It's called The Cosmos Explained up there. It's got pictures in it. It's not a lot of text. It's a fun book. I like it. The U.S. cover price is $25. And if you want to buy it, and I'll sign it, and then I will get my stash reimbursed or replenished by the Ivy Press when I get home the next, okay? And yeah, I think you can get it online, but I don't think you can get it in any bookstores in the United States. I was able to find a Chinese language copy in Taipei a couple of weeks ago, so I know it's somewhere, but that's kind of what I'm doing. I think I have maybe 15, 20 copies back there, so if you want them, I'd be happy to sign them and talk to them. Okay, thank you.
Hi, what can you tell us about the little red dots that were discovered?
Those are great. Okay, if you have heard the term little red dots lately, what that basically means is using the James Webb Space Telescope and using the technique of looking at things that are far away using something called gravitational lensing, astronomers have been able to find a lot of distant objects. We think they're 10, 11, 12 billion light years away from us. But they seem not to be surrounded by any stars. They seem to be just black holes sitting around in the universe. So if there are stars around these little red dots, we can't see them. So this has led to a lot of speculation. We astronomers, we make models, and they're mostly correct. They explain what's there, but they're incomplete. We have always thought that in order to have a black hole that far away in the universe and that visible, there had to be stars first. The stars had to form at least at the same time, if not earlier than the black hole. So every supermassive black hole at that time should have a galaxy around it. The fact that these little red dots seem not to have a galaxy around them sheds a lot of insight onto whether or not black holes formed on their own without a galaxy to host them. There's other evidence folks like Priya Natarajan at Yale have found. They have found actual galaxies and supermassive black holes that are so old and so massive that we can't use our own current models of the universe to make a galaxy before we make the black holes. The black holes have to come first, right? This is a very exciting result, but it's not yet confirmed yet. It's probably, reliable at the 70% level. We don't have it at the 95 or the 99%. And so these little red dots just continue to add to that mystery. It is my belief that in the next year or two, as Nancy Grace Roman looks, we're going to find even more of these. And then once we get some decent statistics on how many of these little red dots there actually are, where they're distributed in the universe as a function of cosmic time, we will be able to answer the question, did black holes form before stars themselves? Good way to end, right? Thank you so much again. It's been such a pleasure.